So, hello Laura and Max and anyone else watching at home. Sorry, you've joined us in the middle of paper 1 from 2021, question 11. We've just done the trapezium rule first part. Please let me know if you need a reminder of the trapezium rule. And we're about to integrate this function algebraically. So the function is ln of x squared, and we're going to integrate it to see if we can write the answer not as a decimal like we've just done with the trapezium rule, 2.41, but they want it in this rather convoluted form. So, could anyone propose how I could rewrite the function to make it something I can integrate? Go for it, Sean.
1 times ln of x squared.
I'm not actually going to do that, but if that works, does it work? Good. I was going to do it this way.
ln of x times ln of x.
I was going to write it as the ln of x times the ln of x. I'm interested to know whether my way's harder work or easier than... So what I'm going to do is use integration by parts. We've already used integration by parts once today, and both of the things in the windows are going to be ln of x. And again, for Laura and Max, in our starter, sorry, I meant to start the camera earlier, we've already said that when you integrate ln of x, you can write it as 1 times ln of x and use integration by parts. You get that, so I can, and I know when I differentiate ln of x, I get 1 over x. Okay, you're on your own now. This is a little bit fiddly, but see if you can use integration by parts from the formula sheet, same page as the trapezium rule, and get me an answer. Okay? See, don't forget we're then substituting in 2 and 4. So I do u times v, this is from the formula book, which multiplies out to give me that, which looks horrible, but the question asks for it in this form, so I'm okay with that.
Where's your 1 times 2?
I've then got 1 over x times that, which gives me this, but I've got to watch out for that minus sign. So I'm going to put that minus sign with brackets. The integral of ln of x, there it is again, and the integral of minus 1 is minus x. Sort out the minus signs to get to there.
You can't bring that 2 down if it's outside the ln. See, it's not ln of x squared, it's ln of x squared.
So what we now need to do is substitute in 4 and 2 to that, and do what you get when you substitute in 4, take away what you get when you substitute in 2. Didn't check your pluses and minuses. Were you?
Yes.
Were we in agreement?
Yeah, you just need to be careful when expanding the negative end.
Yeah, just be careful. This isn't the ln of x squared. It is the ln of x squared. And we've got a little bit of a problem because they want it all in terms of ln2. I'm going to have to flick between the two, but so when we've got ln4s, we've got to think, how can I rewrite ln4 as something to do with ln2? Anyway, I'm going to leave you to puzzle over that just for a minute. My brackets are nowhere near big enough, are they?
Minus 2.
how am I going to rewrite ln of 4 so it's a bit more twosy? Can you write 4 in terms of 2?
2 squared.
So ln of 4 is the ln of 2 squared, which is 2 lots of the ln of 2. That's using that third log rule. And the ln of 4 squared, therefore, will be 2 times the ln of 2 squared, which is 4 ln of 2 squared. That's just like 2x squared. 2x times 2x is 4x squared, 2 ln 2 squared. So I am going to rewrite, and I've actually got 4 lots of that. So 4 lots of that will be 16 ln of 2, and I've got 8 lots of ln 4, which will be 16 ln 2. So I'm going to rewrite it all. So that's going to become 16 ln of 2 squared minus 16 ln of 2 plus 8. I've then got minus 2 ln of 2 squared plus 4 ln of 2 minus 4. We're nearly there, promise you. So we've got 14 ln of 2 squared minus 12 ln of 2, 8 take away 4, plus 4. He nervously moves to the mark scheme. Check the answer. Well, it's a miracle. There we go. Now, please be clear, I'm not doing that question because it's easy. Not in any way. I just thought it was a really good question in that it involves trapezium rule, integration by parts, this particular trick using integration by parts, a bit of log action. There's a whole lot going on. I can well imagine in the examiner's room when these dusty old men and women had written that question, they were all patting themselves on the back. Oh yeah, well done, good job, good job, good job. You know, there's a whole lot going on there. Right. It's quite fun when people ask me to help with questions because I know when you get stuck it's going to be something really hard. So I'm thinking, oh dear. You know, so there's another one I'd quite like to go through to do with modulus. So I'm going to juggle things around and we'll do some modulus. But we are going to do some parametrics first. We haven't done any parametrics for a while. So I'd like to spend a chunk of what we've got left talking about changing parametric functions to Cartesian. And then if we've got time, we'll move on to some differentiation of parametrics. We won't have time to do any integration by parametrics, which we will also do though at some point. So let's talk about parametric to Cartesian. So just a reminder what we're dealing with here. Normally when we are given a rule, a function, it's written as y equals something to do with x, or maybe f of x is equal to something to do with x. But occasionally it is easier to define the x and the y value separately. For example, when we're talking about projectile motion, it was much easier yesterday to deal with horizontal and vertical motion separately, and so this is a bit of a crossover here. But when we do that, both functions are in terms of some parameter t. Now, in projectiles, t is time. The definition is changing with time, but sometimes t is an angle. And you get some weird and wonderful curves described using parametric form, and they are generally, equations are written in parametric form because they look really complicated as Cartesian functions, but sometimes we're expected to transfer between the two. And there are two main cases, okay? You've got simple and you've got trig. And you know, as we all know, trig is rarely simple. So if we haven't got trig and we've got two Cartesian functions, we do it by replacing the t in one equation with the t from the other equation. Now sometimes we do that by rewriting one equation as t equals. So for example here I could rewrite this as t equals the square root of y. However, in this case you can actually do it a little bit more quickly. But what I'm going to do is rewrite this equation using this equation. Now that's going to give me an x equals rather than a y equals equation. Perfectly okay, unless they explicitly say in terms of. Just see if you can see what I mean by doing that. I hope you can see that if y is t squared, then t to the power 4 will be y squared. And we're more than capable of doing whatever algebra we would need to rewrite that as y equals, but unless it's specified, that's Cartesian. Okay? So I've sort of misled you by saying Cartesian is y equals. It isn't. Cartesian is where the y and x are relationship is described with a single function, whereas parametric is described as two. So that's simple. I would earnestly wish that a simple one comes up, but it's more likely to involve trig. So let's look at a simple trig example. Sorry. So as soon as trig is involved, don't think, right, I'm going to rewrite one equation as t equals and substitute it into the other. Instead, we use identities. So here I've got one equation with sine and one equation with cos. So I just need an identity that involves sine and cos. And it's always going to be, if it's just sine and cos, I need to do a little bit of algebra here. I need to rearrange that as sine t equals and square it. I need to rearrange that as cos t equals and square it. And then I need to write them all together and make them equal to 1. So just see if you can do that one for me. Max. I was videoing for you. We're talking about, we've done an exam question, which is in the can, as they say. Actually, that also means in the toilet, doesn't it? It's not in the toilet, it's definitely on the toilet. But now we're talking about converting parametric to Cartesian. So sine is x divided by 3. So sine squared is x squared over 9. Cos is y divided by 4. So cos squared is y squared divided by 16. And unless it says in the form whatever, that's okay. That is an equation involving x and y. Now, if we wanted it to be written without fractions, we'd have to find the lowest common multiple of 9 and 16. 9 times 16? Probably is, isn't it? But there we go, there we go. Okay, so that was simple trig. Are we ready to go with moderate trig? So moderate trig will involve the double angle identities. So before, when we had just sine and cos, we used sine squared plus cos squared equals 1. Now I've got cos 2t and sine t, and that's good news because I know that there's all manner of cos 2x or cos 2 theta or cos 2t identities, one of which involves just sine. Now, it's a while since we've done an ILAB trig sheet. Perhaps it's high time we did. I'll have to copy some. But if I remind you that the one I always remember is that one, and I'm hoping you can therefore replace that to make it in terms of sine, and therefore I'm hoping you can work here. Again, you'll have to rewrite that as cos 2t equals, and that as sine t equals. Have a go. Have a go. So cos 2t is y over 2, and sine t is x over 3. So sine squared will be x squared over 9, so it's 2 lots of that. And again, I could double everything, multiply everything by 18. You know, there's all manner of algebra we could do, but that's fine. That's fine. Let's just have a pause while we're talking about identities. Can I ask you to write down the 2 reciprocal identities? They're the ones you get by taking sine squared plus cos squared equals 1 and either dividing everything by sine squared or dividing everything by cos squared. Just just before we get to intermediate difficulty. We've got moderate difficulty, so we'll have intermediate trig. I mean, if you can remember those, then, you know, hats off to you. I can't, so I always have to derive them. So you get sine squared over sine squared, which is 1, cos over sine, which is 1 over tan, so that's cos squared, and 1 over sine squared is cosec. Remember, the third letter reminds you that cosec is 1 over sine, sec is 1 over cos, cot is 1 over tan. And here we've got tan squared plus 1 is 1 over cos, which is sec squared. Right, so intermediate trig is our ones that involve that. So, for example, y equals tan t, x is cos t over 3. Now, neither of those identities involve tan and cos, but sec is 1 over cos. So if I could write this as cos t equals, then sec t will be that flipped over. So I'm going to use that identity there. See if you can. Join the fun. Cos is 3x, so sec is 1 over 3x, so sec squared is 1 over 9x squared. So we have used our really simple identity, sine squared plus cos squared is 1. We've used one of the cos 2x identities, and normally that's harder, but actually, because there are so many cos 2x identities, actually, parametric to Cartesian involving cos 2x, it tends to be easier, because whether you've got cos or sine, you can use it. We've used one of the reciprocal identities. So ironically, nasty trig tends to be ones that involve the sine 2x identities, which is normally the easiest because there's only one way of writing it. But let me give you an example.
Just 'cause-
Now, I guess the one good thing is the fact that there's a sine 2t there. It's got to involve this identity. There's only one sine 2t identity. 2 sine t cos t. Normally we have theta, don't we? Sine 2 theta is 2 sine theta cos theta. And I've got a sine theta. That's all good. But I haven't got a cos theta. Now, there's a couple of things we could do. Let me start you off with one of them. If x is sine t, then x squared is sine squared t. What I'm missing is an expression for cos t. So go on, see if you can follow that to give me an expression for cos t. We've got sine squared, so I'm hoping you can get cos squared, so I'm hoping you can get cos t. However, there's a little bit of a problem. There's a little bit of a problem. See if you can get somewhere with that.
How would you square it? Is that how you present it? Like,
Well, what we're actually going to do is we're not going to use this approach at all.
oh, okay.
I'm going to use a slightly different approach, which does involve squaring. And it involves squaring this. So if x is sine t, then x squared is sine squared. Cos squared is 1 minus sine squared, so that's 1 minus x squared. So of course it's the square root of that. But that could be positive or negative. Now, we might be lucky. They might have told us that the angle is acute. And we know that between 0 and 90, all three, sine, cos and tan, are positive. So we haven't got to worry about it. Or they might have told us that the angle is obtuse between 90 and 180, in which case we know that cos will be negative, only sine is positive. But if we aren't told that at all, we've got a bit of a problem. So let's rewind just one step and instead turn to here. What I'm going to do, and this is a good trick to remember, I'm going to square both sides of this equation. Now, this, we just square it. We write it as sine of 2t squared, which we write as sine squared 2t. What I've got here is 2 times sine t times cos t, which if I multiply by itself, gives me 2 times 2, sine squared times sine squared, cos squared times cos squared. Now, it's easy peasy. I can use those three things to change it into something that just involves y and x. Remember, sine squared 2t is the sine of 2t squared. So you've got to rearrange that top equation first. I could choose to multiply both sides by 16 to give me y squared is 64, x squared. I can multiply it out. There's a whole range of things I could do there. So we've looked at basic and then a whole range of trig. Maybe there's one that doesn't quite fit into the selection. So we've got maybe E and ln. It's as of the first type where it's easier to rewrite as t equals, but sometimes the e's and the ln's cause us a little bit of problem. So we'll finish with this one. Can you and I'm going to tell you how I'd like you to have a go. So I'd like to try and rewrite that first equation as t equals, and then substitute it in there. So you've got to remember how you undo logging, ln. Oh no! Just crashed. Sorry. I have to rewrite it over here because it's crashed. So to undo ln'ing, you e both sides, take away the 1. Just out of interest, what if we needed to expand that? So go on, just grid out what you get if you do e to the x minus 1 squared. What does that actually give you? Because that involves an important point. What do you reckon, Callum? What is e to the x multiplied by e to the x? E to the 2x, yeah. We add the powers. So well done if you got that. So that means we've got e to the 2x minus 2 lots of e to the x. We've got plus 1, but then we've got a minus 5. So there we go. And that is a quadratic in disguise, isn't it? That's a quadratic in disguise. There we go. That's another lesson.